So let me say, remember last time we started, so yesterday, we started setting up the geometric background which will be needed to pursue the whole story. So we want to understand, given a general morphism, what we want to do is find ways to find additional data that will provide us for some or any factorization x in M in Y with a locally free sheaf I subjecting I mod I squared, where I is the ideal sheaf of X in M, and in such a way which is compatible with different factorization. So the part of the point is, in fact, we cannot quite do that, but what we have to do is we have to geometrically work with complexes. So this object here has the problem that it depends on the factorization. So instead we want to work with something which does not depend on the factorization, and so we choose to work with what we call the L triddle of F, which is a well-defined element. Well, in general, so here, and this is just the complex I mod I squared to I pull back of omega my. And this is well defined. It doesn't depend up to canonical isomorphism, well defined up to canonical isomorphism. And in fact, this is already one direction where we go beyond the book of Fulton, because in fact this L triddle F exists for any morphism of schemes. And it has, with the property that it commutes with, it is local in the Zariski, but also in the et al. And smooth and flat topology in Y, or if you, and it's local in the Zariski et al. Topology in X. This means if you base change, it pulls back. And so in particular, we don't need any assumptions, and it's a very general, it is just the cutoff of the cotangent complex as defined by Ilusi. Cotangent complex. So we will, so the point is, we have this explicit interpretation, but there is a more general one, which is based on taking simplicial resolutions, and I want to leave it at that. So, but we will mostly be interested in cases where this actually exists. So now what we want to do is we want to have, in particular, what we want is we want a morphism. So since we want to work directly on X, so what our aim will be is to find conditions on morphisms of in D minus 1, 0, co-x, so E dot to L twiddle F dot, and sometimes I put a dot and sometimes I don't. So what I mean is I put a dot when I want to insist that this is a complex. So not, it's just a very short complex, but a complex nevertheless. Such that E is quasi-isomorphic. I mean, I was told quasi-isomorphic is not an adjective, so let me say is isomorphic in the derived category to E minus 1 to E to I pull back omega my, where, and the morphism is given under this isomorphism by with E locally free and E to I mod I squared surjective. Well, so before I start, I want to say that I don't know how to do it globally. So we will really need to find out the stacky construction will allow us to do things slightly differently, to check that this, to find something which is global and which doesn't change under quasi-isomorphism. This is what.
So curly E is not one of the pieces of curly E dot.
I don't have a curly E dot. Ah, sorry, no, this is another one. Sorry, this, let me, yeah, I don't know how to call it. Sorry. It is not, well, it is because this is an incarnation, but yeah, it's not quite the same.
So, I mean, yeah, so curly E dot could be, so this could be E
Let
dot.
me just call it F.
Okay.
So then we are done.
And there also is to the last line.
Yes. Yes. So what I want to do is, before I do this globally, let me start to do it locally. This is because, you know, locally I understand what's going on. So let me consider, first of all.
There's a question.
Yes?
I think I also know the answer, so I just realized the answer.
Okay. But you maybe still want to ask it, because if you ask yourself a question, others will.
Okay, so the question was, if you're going to do such constructions locally, even if you have a co-cycle rule, even if you have a co-cycle rule, you cannot patch because it's not complex. But I understand why you're doing stats. So
Yes, so exactly. No, that exactly. So the point is, what I want, the conditions I'm interested in, namely that this F be locally free and that this morphism be surjective, is obviously a local condition. On the other hand, as was made evident, the derived category doesn't glue well. So you cannot define, I mean, there are ways and means. I know whom to ask when I have to do a gluing in the derived category, but it is an unpleasant thing and only happens in lucky cases. So what we will do is we will split the problem into two parts. So this condition is clearly something which can be checked locally, and that we will do today. And then on Thursday, we will go back, we will take again this approach by Deligne, we will define what a quotient stack is, and we will see how the stack, there is this general approach that starts with a general object in the derived category and brings to us a general geometric object, which then you don't have to glue because it comes pre-glued. So you have the linear do your gluing for you, which is kind of nice. So, and by the way, there is one imprecision here that it exists for any morphism of schemes, but let me, it should be written directly, it exists in general in the X, so in the derived category of OX modules, and if F is locally of finite type, then F is, so I only have that the cohomology is coherent, but in general I don't know that I can represent it globally as a morphism of coherent sheaves. But that's so much more important that when we work locally, so we have two different conditions. This condition here doesn't have so much to do with the map, and it only has to do with a complex. It means locally I can write it this way. And the second condition, of course, has to do with the map. So the first thing is the following, that the following remark, that assume I have a quasi-isomorphism, so let me write it, E dot goes to F dot is a morphism of complexes. So remember I had my category B, so and inside B I had this more special category, which I should have given names. So let me recall that. We had a category B where the objects were morphisms of coherent sheaves, and the morphisms were commutative diagrams. And inside this, we have a full subcategory C, which is the same, but with a condition that F0 is locally free. And what we have is we have a map from C to B to D minus 1, 0 co X, which is just viewed, well, this is just the inclusion, and this is you take a morphism like this, and you map it to the complex with just zeros elsewhere. And what we had seen, or what I had told you is true, is that, well, this here, and indeed this here, is essentially surjective. So that every, if X has enough locally frees, then C in minus 1, 0 for X is essentially surjective. And what I want to show is, let me consider let us consider a morphism phi from E dot to F dot in C, which induces an isomorphism in the derived category. Well, then lemma, then E minus 1 is locally free if and only if F minus 1 is locally free. And this is, so in particular, this is a property which only depends on the object in the derived category. And this condition is when either is true, definition, when the corresponding object in D of x is called perfect of perfect amplitude contained in minus 1, 0. So, and of course, there is a more general definition where it's perfect of perfect amplitude contained in AB. It means that it is locally isomorphic to a sequence of locally frees in degrees A to B, and everything else is 0. So how do you prove the lemma? Well, basically what you do, this is a local, the lemma is local, the condition is local, proof of lemma. So the condition is local, so you may assume that x is affine, say equal to spec A, and that E0 and F0 are free. And then it is an F0 are free, and then you assume, for instance, that, and say E minus 1 is free, and you prove F minus 1 is locally free, and conversely. So what you do now, for instance, yeah, so this is what you have is you have your easy, you.
So what is the last line? Perfect of perfect amplitude?
Sorry?
Is called perfect of perfect amplitude?
Contained in minus 1, 0. So in general, perfect contained in AB, in an interval AB, like 2, 5, means locally on X, I can write the complex, the restriction to every point has an open subset, an open neighborhood such that the restriction is of this form, of a sequence of locally frees. In fact, if you take it locally, you can also take them free. So what you do is if you take them free, then what you can do is you may assume, again without loss of generality, you may assume that E0 to F0 is surjective, and then what you get is that the diagram must be Cartesian, and then you get that, and you prove that F minus 1 is locally free. So this is up to changing e's, both e's by adding a free factor, which is not a problem because you can add a free factor without changing the quasi-isomorphism class. And of course, if you have a sheaf and you add a free sheaf and it becomes locally free, then it was locally free to begin with. And you get that, and then you get that if F minus 1 is locally free, then so is E minus 1, and conversely. Basically, you get an exact sequence 0 in E minus 1 in F minus 1 plus E0 in F0. And then if these two are locally free, then this is locally free if and only if this one is locally free. Okay, so that is the lemma. So the first condition, so the condition that when I write it in this way, the F becomes locally free, is just a condition which we can write simply in an abstract way by saying it is in some representation locally a morphism of locally frees. And there are conditions under which this is true. So let me give you an example of where do you get something which is locally free of So let me give you an example. So assume pi from, I want to have now, so from x, from z to x is a flat projective morphism, and f in co-z is flat over x. Then what you can do, well, from Hartshorne you know that you can take the higher push forwards. So the derived category version of cohomology and base change tells you that, says that there is a well-defined complex R, and this is really total push forward of F in D co X, which is perfect in 0R, where R is the relative dimension of Z over X. And moreover, if I can, for instance, if I know that HR of Zx, this is the fiber over a point little x in X, F restricted to Zx is 0 for all x in X, then it is perfect in 0 R minus 1. And so on. If I know that the H R minus 1 is also 0, then it's perfect in 0 R minus 2, and so on. So it is not terribly difficult to find perfect complexes so long as things are flat. And a way to see this is that yeah, it writes it like this, but he doesn't use this language. Yes. Yes, he uses, so certainly the complex is written down in the proof of, also, of course, it depends, Hartshorne has written many books, depending which books you read, you get also this version, but okay, wonderful. That's great. That's why I want to give this talk in front of people who have actually, read the classics. So the good reference for this would be Mumford abelian varieties. Because actually this is great. Actually, this thing that there are more, I mean, one of, yeah, anyway, there is one point in GIT, for instance, which is an incredibly important version of cohomology-based change, and the title is something like proof of 4.7 or something completely uninformative. I mean, it's not always easy to find what you want in the classic. So anyway, the point is that this condition is actually pretty easy to come by, or it's false, but I mean, if it is true, it's usually an easy one to verify. So let us go to the second condition, and the second condition was this subjectivity. So the idea is, remember, I want to describe this as a condition in the derived category. So I want to say it in terms of, for instance, cohomology groups. So what does it mean that this is surjective? Well, what can I say about the kernel and the co-kernel? And as again, this we already mentioned, there is lemma that given a commutative diagram of coherent sheaves E minus 1 to E0 if E0 to F0 is an isomorphism, then E minus 1 to F minus 1 is surjective. So let me call it this F minus 1 and phi 0. Actually, here I usually prefer to put the indices below, because this way, if I need to invert a map, I still have space. This is surjective if and only if the induced, so let me call this DE and DF. So the induced map from the co-kernel of DE to the co-kernel of DF is an isomorphism, and the induced map from the kernel of DE to the kernel of DF is surjective. So this is kind of very simple. You split each sequence in image co-kernel and you chase all the diagrams, and this is just proof. It's just a very elementary algebra exercise. So this means that once I have such a local representation, the condition on surjectivity becomes a condition that I can really write in the derived category. And of course, if I want a surjectivity of a morphism of coherent, of a homomorphism of coherent sheaves, then it's very clear that this surjectivity exists if and only if, remark, and this is also completely obvious, we also mentioned it last time, lemma, if F to G is a morphism in co-X, then F is surjective if and only if for every X in X. And remember here, I usually like to think of X as finite type over a field, and when I write this, I mean over the closed points. the induced homomorphism of vector spaces fx tensor
You mean F is surjective?
sorry, phi is surjective if and only if the induced map on the fibers is surjective. So I can forget about all this story, and all I care about is understanding what is happening here and how I get this stuff to work. And now my question is, how do I get, so this means in some sense, all I have to control is a number of vector spaces here, which means I want to see what is happening. And the answer, how do I get a hold of understanding the fibers of this kernel? And the answer is, I want to get an understanding of this by working on with fat points. So from here on, I will assume for the rest of today, I will assume that all schemes are of finite type over the complex numbers or an algebraically closed field of characteristic 0. There is a version over an arbitrary field, and there is even a version without base field. I will try to include it in the notes, but the point is, the more general you want to do it, then you want to write, there is the general language of the formation theory, but what I want to do is this case because it's really very elementary. So let me start by some parts where this will not be necessary. So let me start by saying definition. A fat point is a scheme S such that if I take S red and I map it to spec C, because it's after all a scheme over C, this is an isomorphism. And so it's just a point with some non-reduced structure, and of course it's a remark that the category of fat points is dual to the category of, is equivalent to the category of A C algebras, local C algebras, such that say, for instance, A is finitely generated and Artinian. This is probably redundant. Or if you want, this is equal to A local C algebras such that the dimension as a vector space of A is finite. Or this is also A local finitely generated C algebras such that the maximal ideal is nilpotent. So the point, as I promised, is we can use these flat points to study the smoothness or not of morphisms of schemes. And the place where you can read the general case is, for instance, the book of Milne. There is one part about where he discusses formal smoothness and formal etalness. And the point is that in the condition where everything is of finite type over a field, formal smoothness and smoothness are the same, and the same for etalness. So the first thing, I also want to give some more definition. Let S1 in S2 be a closed embedding of fat points. So this corresponds to an exact sequence of algebra. It's a closed embedding. So A2 to A1 is a surjection in that category, and I is the kernel. We say it is a square 0 closed embedding, square 0 if I squared is 0. We say it is semi-small if I times the maximal ideal is 0, and it is small if the dimension as a C vector space of I is 0. Well, it's 1, thank you. So this condition clearly implies this one, because every ideal is in the maximal ideal. And on the other hand, this condition implies this, because when you multiply by A, the 1 has to go isomorphically, and it's already surjective, so the rest has to go to 0. And in particular, this, if I view it geometrically, this means that the ideal of S1 in S2, which a priori is a coherent sheaf on S2, is a push forward from S1. And this condition is that this ideal is a push forward from S2 red, which is of course equal to S1 red. Okay, and then we have a very easy, we have a very few easy lemmas in algebra. Lemma, let zero in I, in A1, in A2, in A1, 0, a square 0 extension. If I view it as algebras, I call it extension, and if I view it as a schemes, I close this closed embedding. And let P be an so let us give, let R, yes? This is an I.
No, that's the kernel. This is the ideal of S1.
This is the ideal. So I is the kernel here.
Is that right? What is TS1?
Oh, sorry. This is, I'm Italian. This is Methcal I. I'm sorry, because this is, I can learn many things. I learned this in 1972. I don't think I can unlearn it anytime.
So
sorry. Yes.
I started with a T.
Yes, no, but it's really a problem how you write letters, that Italians don't write letters the way English do, and I think the way Indians do, because Indians write these letters the way they learned from the Britons. And I don't know which parts of Europe write an I like this. Probably only we do. But just for the record, it's like when in English, when you have a cal I, it looks like this. And in Italian, this looks like an O. It doesn't look like an I at all. And if I want to write a T, I would write it like this. Sorry about that. So this is, typically this is O, and this is T. And I cannot change it. So this will be always the case, that this is a mathcal I, and that it cannot be helped. So let R be a C algebra, and P and is there a, all right.
The square extension means I squared 0.
It means that I squared is 0.
There, in the first line is square 0. Square 0, semi-small, small.
Okay.
Increasing order of thickening.
And assume we have. Yeah, so somehow, actually, I'll say something in a moment. I should have said it here. Assume we are given a commutative diagram of algebra homomorphisms. So I have R to P, since P is an R algebra, and then I assume I have a diagram like this. And I ask myself whether I can find a homomorphism of algebras like this, which makes the diagram commute. So let me call this alpha, and by saying that it commutes, it will mean that this composition is this, and this composition is this. So what I claim is that the set of alpha as a homomorphism C algebras from P to A2 such that the diagram commutes if non-empty, I'm not assuming it's non-empty, is a principal homogeneous space under hom R omega P over R I. So notice that I is an A1 module. Sorry, this is not hom R, this is a hom P. I is an A1 module by assumption. So this means that it is a P module. And this, of course, is a P module by definition, so this makes sense. And this is one of, this is kind of the basic idea of how the cotangent sheaf plays a role in when you work y square 0 batches well, and the proof is very easy. So assume that it's non-empty, because if it's empty, there is nothing to prove. So choose an alpha 0 from P to A2, which makes the diagram commute. So now let us consider an arbitrary map alpha. I take the set of alpha from P to A2 such that the diagram commutes. And I map them to the R linear to the homomorphisms from P linear homomorphisms from P to I by saying, well, if I have an element here, I can map it to alpha minus alpha 0. Since the two have to commute, so I have P times A1 is given. If I have two maps which have the same image here, then the difference must go into here. Exactly. And the question is, let me call this lambda, so I can try to do the converse. So the conversely, so that what you need to prove is that lambda is there is an R derivation if and only if alpha, which is alpha 0 plus lambda, is a morphism, a homomorphism that makes the diagram commute. And the point is that what does it mean? Of course, that the diagram commutes is the same. It says that the difference goes to I. So this is clearly, if I just took R linear maps, then this would be true. And the additional condition that this is an algebra homomorphism becomes that the lambda is a derivation. This you just write down the condition that alpha of P1, P2 is equal to alpha P1, alpha P2. You write down the product, and at some point you are left with one bit you can't manage, which is lambda of something times lambda of something else, and you use that I squared is equal to 0.
Last slide. If I is A1 module implies what?
A1 module.
No, that implies what?
That it is a P module. So what I want to say is that this actually makes sense. Before I prove that it's true, I want to show that it is actually a well-defined element. So if I want to do hom, I have to have two modules over the same ring. Okay, so this is kind of an extremely elementary thing. If you have never done the exercise, I suggest you do it, and if you have done it, you don't have to do it again. Notice that here you just need I squared is equal to 0, and this thing is so canonical that in fact it has a counterpart for arbitrary schemes. I mean, you don't really need affine schemes here. And now what well, it's interesting, but what does it have to do with our problem? And now what I want to write is the following proposition. Let f from x to y be a morphism of schemes, and let S1 into S2 be a semi-small extension, closed embedding of fat points. Assume given a commutative diagram, and I'll write it in the next blackboard. So I'm taking this diagram here of algebras, and I'm reversing it completely to be a diagram of schemes. So I have to, of course, turn all the arrows around. So I have S1 in S2, and this goes to X, and this goes to I. And I also let x in X be the point defined by S1 red. Well, this, remember, is spec C. Well, this is inside S1, and this goes to X. So you have, to such a diagram, you can associate a point, the point which is the image of the only point here. Then there exists a natural obstruction to the existence of an alpha making the diagram commute in, and I have to tell you into what. So what I do is I consider the map O into the co-kernel of home. So remember, I have my x, I can factor into x in M in Y, and I get a complex I mod I squared into omega I pullback of omega M over Y. This is my LF. And this is a complex on X. So these are coherent sheaves on X. So what I can do is I can pull them back via this map here. So here I have a spec C. This is X. So this is just a C vector spaces. X pull back, I pull back, omega M over Y to I to home, always C, X pull back, I mod I squared. Sorry, this, let me call this kernel J. This I had done, and then of course I forgot. And this is J, and this is J. I want, I should have changed this one. Okay, keep that as it was and call this J, so that I don't go into trouble. Yeah, I know it's a math something, but let me just call it J. Keep the one before as it was, and here J is the ideal sheaf. This way I don't have math calcs around of X in M. X pullback I. So where this map is of course induced by J or J squared. Sorry?
Really, but in the co-kernel that within the brackets, the capital I should be curly I, right? Because that's a sheaf.
No, capital.
I should be.
No, this is a vector space.
Yeah, right. That O is of sheaves.
No, that I is that I is a sheaf.
You become confused with
That I is a sheaf. The I there on that board is a sheaf.
So
No, this I is good.
So this is a sheaf. So if you want, you can call this calligraphic, but
The problem is not with J. I just
AI is a vector space because I'm assuming that the maximal I is semi-small, so this is just a C vector space.
Is that the same I?
Power, that should be
Yes, yes, now I've decided that I leave everything as it was because I think it's easier than changing them all. I just said it, but I didn't do it.
My doubt was that home is a home of sheaves.
No, this, well, okay, it's a home of coherent sheaves on spec C. And then I identify a coherent sheaf on spec C with a finite dimensional vector space. And I trust that this is not, and this is just C linear. So if you want, is a home in co-spec C, but I pulled back all the way. So, and what I, okay, so let me try and write a proof. So the first step is to notice that in this discussion, all this will not change the problem if I replace either y with an open neighborhood of the image of the point or x with an open neighborhood. So I may as well assume that x and y are affine. And moreover, by all the arguments we had about this complex, that this really doesn't depend up to adding kind of a trivial a free factor or locally free factor on each side. This doesn't change either the kernel or the co-kernel. So this means that may assume that a result does not depend on the choice of factorization. So I can choose whatever factorization I find convenient. And now I have that y is affine, x is affine, and everything is of finite type over the complex numbers. And so what I can assume is that I factor, you know, that y is spec R, and x is a finitely generated R algebra. And what I do is I assume that M is spec R of x1, xn, and then I write x, let me call it just a spec p to say it's a polynomial, p as polynomials, and this is y times an, and then I assume that x is of course given by spec p modulo j. Again, before I had that it was an ideal sheaf, but now since we are in an affine context, I use the same letter to denote the corresponding ideal. Okay, so the first remark, so let me write the diagram in which I take into account the So let me write the diagram again, and now I have S1 to S2, then I have Y, X, P, and I have two questions. The question is to study my original question is whether I can find an alpha here, sorry, M, an alpha here that makes the diagram commute. But of course I can also, as an intermediate question, study the set of betas, because if I can find an alpha, it certainly will induce me a beta.
You assume that a certain diagram continues. What are you going to call the lifting map here? In a proposition,
Yes.
in an infinitesimal situation, you have a diagonal
Yes.
That's, we're not going to call that alpha.
Well, the question is whether such an alpha exists.
So this is when you go past, when you have x and y.
Yes.
When you have a1 and a2. When you see the hypothesis, when you say that.
Oh, okay, it's not the same alpha. Well, let me go back here. So that was a theorem about algebras.
But when you say given a commutative diagram, do you include?
So what I say is I'm given the white diagram and I ask myself whether there is a red arrow which makes the diagram commute. That is that is good that I say it. So this is always the case because this will happen again and again, that the question is the data is the white and the colorful chalk are the thing which I don't know whether it's there or not. But I want to still, so normally in traditional math books it's written as broken arrows, but once I have colors I find it easier to write it in colors. So the point is, a priori what I know, so what I have is that the set of alpha from S2 to X such that the diagram commute. Well, a priori it has a map to the set of betas from S2 to M such that the diagram commutes. But in fact, this map is injective because this is a closed embedding by assumption. It's injective since X to M is a closed embedding.
M2I is smooth, no?
M2I is smooth, exactly. Well, it's even better than that. It's not just smooth. I'm assuming that I've decided to use my complete freedom and have a product. So, you know, this is algebra for the non-algebraically gifted. So now you want to write the same thing and this time with algebras, so A1, A2, P mod I, P R. Okay, so I'm rewritten the diagram in the algebra description. So now I take the set of all P to A2 such that the diagram commutes. And this is clearly not empty because P is, you know, free. So anything will do. I just take n free elements here that lift the given ones and I'm fine. So this is non-empty. And so by the lemma, this is a principal homogeneous space. Well, before I get this is P to A2. And of course, from if I have such a map from P to A2, remember this comes from, I know that, so let me write 0 goes to J, goes to A2, goes to A1, goes to 0. Or let me check, no, this was J, and this was I. Okay, and then I have my P mod I goes to A1 and P mod J, and this is J. So in particular to such a map, of course, this induces a map from J to I. So this maps. So this is just a set, notice, it's a set, and this maps to homomorphisms from J to I. What property do these morphisms have? They are P mod J linear. which in particular tells me that they go over j mod j squared, because j squared maps to 0. So that is not a problem. And now what you have is that P mod j omega P over R I acts on each of these. It acts here by translation, by this homomorphism, and it acts here because this is what we said. And we know that this is a principal homogeneous space, which means that what I know is that if I go to here, to the co-kernel, and I will not write it all down, but it's a co-kernel of this map, then if I start with element here, and I go here, then the result will not depend on which element I have started. And given two elements here, they will have the same image here given one element here which is in the image, then another element will be in the image if and only if it goes in the same element here. So now the question is, so let me call this map theta, and my question is whether I can do the factorization. So the question is, does the image of theta contain 0? And this is if and only if alpha exists. So image of theta contains 0 if and only if alpha exists.
So it becomes the base point in some sense.
Sorry?
It becomes the base point.
Yes, if it exists. Well, it needn't be a base point because it may not be unique. Even if I have something which goes to 0, it doesn't, the ones which will go to 0 will be a principal homogeneous space under omega p over I to R. So it's, but so I never have, so that's a problem, that this guy here is really, it's just a principal homogeneous space. Normally there will be no way that you have a special point in it, even if if it's not empty, but it really is just a principal homogeneous space. And so if and only if alpha exists, and this is if and only if for any beta from P to A2. Of course, I should call it beta upper star, but I denote with the same letter a morphism of affine schemes and the corresponding morphism of algebras. For every beta, its image in the co-kernel is 0. Because if I start with any element, it goes to something here, and if the image here is 0, it means there is an element here which have the same image, and so I change it, and then I get something which actually maps to 0. So let me make a few remarks about this. So this tells me two things. Well, first of all, it tells me that corollary, well, let x to y is smooth, well, if and all, let's say implies, then it's easy to prove the other implication, but in particular it implies that for any diagram there exists with S1 in S2 a closed embedding of fat points, the diagram, there exists an alpha such that the diagram commutes. Because, of course, if it's smooth, I can take as factorization that just x is equal to m, then this is 0, and then there is no co-kernel. And in fact, so this is what is called as saying that smoothness implies formal smoothness. And then what you have to check, and what you can easily check, is that in fact, remark, the converse is also true. But in the moment I'm not interested in this, so I will not say it. So the point is that another way of saying this, sorry? Well, we have always assuming that everything is of finite type over the complex numbers. So it's definitely true in this case. But the point is, in fact, as you can see, a lot of this proof will extend to much more general case. And to have the converse, you need a finite type assumption. But in all our cases, things are of finite type, so things don't go bad. You just have to be a bit careful with the proofs, with the residue fields, if you have a base field which is not algebraically closed, and if you then you have to keep into account the fact that the residue field point by point may change, so you have to decide what you want to define as fat points. And then the further thing is that if you are allowing non-algebraically closed base field and you are in positive characteristic, then you have to also keep into account whether the extension of residue fields is separable or not. So there is an exercise in Hartshorne. There is an exercise. So a good way to do this is to use, there is an exercise in Hartshorne chapter 3, section 10, which says that, again, under the assumption for schemes of finite type over a field, you have that f from x to y is smooth at x, and this is if and only if the formal completion of x at x is isomorphic to a formal power series, so free formal power series over O y hat over ky kx. Is there a problem? Yeah, well, so the point, the reason, you see, if you go and look at this, you will notice that to make sense of this statement, you have to say that this formal ring is an algebra over the residue field, which if the residue field is algebraically closed and everything is already above that field, it's obvious. But otherwise, you need to pick up a book of commutative algebra to tell you that there is a field of representatives. And that's why I chose to write this over the complex numbers.
You say this is a corollary, but here earlier S1 and S2 was supposed to be at least semi-small.
Oh yes, the point is, remark that this is something I always forget to say, that every S1 into S2 closed embedding factors as a sequence, a finite sequence of small, in fact, or semi-small or square zero closed embeddings. So what you do is you can take A1, A2, and you write it as A1 mod I, and then you have A1 mod Mi, and then you have A1 mod M squared I, and so on. And this sequence finishes. These are all semi-small, and if you want now any vector space quotient will give you a small extension. So there is no, once you can lift the semi-small or the small, you can lift them all. Yes? Okay, so the point is, let me write this separately. Can I erase this? So this is just so if you have called this here M1 and call this here M2 and call this here N. So what you have is M1 to M2, a homomorphism of abelian groups, and you have N, a principal homogeneous space over M1, and theta from N to M2, and M1 equivariant map. So here M1 acts because it's a principal homogeneous space, and here it acts by translation. Okay? And now here you take the co-kernel C, let me call it co-kernel. And what I claim is if I have this situation, then if I take, let me call this map phi is just a projection. So the first thing is 1 for every n in n, for every n1 and n2 in n, pi of theta of n1 is equal to pi of theta of n2, because n2 given n1 in n and m in m2, there exists an n2 in, so this thing here is a well-defined element, which I'll call C0 in the co-kernel. And now, and given an m in m2, there exists an n in n such that theta of n is m, if and only if pi of m is C0. Because if you have two elements in M2 which have the same image, then the difference comes from M1. So if one is in the image of N, then the other also is, and conversely. And in particular, once you put this together, 0 in M2 is in the image of theta, even only if C0 is 0. So, and if, I mean, that secretly, I know that these are vector spaces, and this is an affine space, and I learned vector spaces and affine spaces in the first year, so I feel it very comforting that all the time I spent learning affine spaces plays a role. Okay, so the point is you have this vector space, and this has actually, so one way let me rephrase what, as I said, if you want to write this in detail, this requires a lot of algebra. So I've decided to stick with complex numbers so that everything is as simple as can be. And let me now try to rephrase this in the following way. That, so if you let f from x to y be a morphism of schemes of finite type over the complex numbers, and x be a point, and I always mean a complex valued point, so a closed point. Then to this situation, the vector space and let me call it T2 x f, which is this co-kernel that I had written. So let me say, if you work out what it is, you can just take the case where you have a small extension and you just take C, because remember, we were just taking homomorphism of C vector spaces. So I is just C to the direct sum and so many copies. So this T2 of xf, which will be the co-kernel of the same thing, but with the C just. Sorry, this is the omega, I mean, the co-kernel as before, with I replaced by C, has the property that for any commutative diagram S1 to S2 x in y, such that it's over this point here, such that S1 in S2 is semi-small with kernel I, there is an obstruction to the existence of the usual alpha in T2 xf tensor Ci, which is functorial in a very simple sense that you assume that you have another T1 to T2 and you have another commutative, it doesn't even have to be Cartesian, but it is commutative, and then you have a map between the ideals and it commutes with the natural maps. So in other words, a way to say all of this is that this is a well-known property in deformation theory. This says that T2 xf is an obstruction space for x over y at x. And there is a very, very simple lemma, which again is something that requires, so one implication is, lemma, let me state the lemma, let V be any other complex vector space that is an obstruction space for x over y at x. So this means that for every such diagram I find an obstruction which is functorial. So this is not just the data of a vector space, but it's a vector space plus for every commutative diagram an object such that the lifting exists if and only if the object map is 0, and such that these are functorial in the appropriate sense. So there is an obvious way in which to do it, which is if you take this vector space and you put it into something larger, then of course you just take the image, and if it was 0 it stays 0, and if it wasn't 0, if you enlarge a vector space it will. And the lemma says that then there exists unique, there exists an inclusion T2 XF in V inducing the obstruction. And the way you do it is basically you you write X as you pass to local rings, pass to formal completions, and then you use the lemma of Artin-Ries. So it's just a matter of you take enough algebra and it becomes an incredibly elementary question. The only part is that a power series ring is not an Artinian, it's not necessarily nilpotent. So what you have to do is that whichever property of the formal completions you are interested in will be preserved if you quotient by a sufficiently large power of the maximal ideals. So the idea is that if you have equations defining your subscheme, they will be enough to see how you can see them enough even if you forget higher order terms, which is kind of obvious because each equation is at a finite order. So there is at some point there is enough equations that they determine everything at any order. So this is so why is this important? This is important because in deformation theory you often have something which gives you one obstruction space, which typically will not be the same, but it will be an obstruction space. So you will have an inclusion. But if you have an inclusion after you dualize, this corresponds to a surjection before you dualize. So in other words, the condition on having, remember we had split our problem into two parts. One part was making sure we had a locally free sheaf, and this came from having a perfect complex. And the other part of the problem was to have a surjectivity on the I mod I squared. And this surjectivity will turn out is the same as the surjectivity on the kernels, and the surjectivity on the kernels become an injectivity on the co-kernels once you dualize everything. And so this condition here, the condition that our complex is as good as the cotangent complex as far as deformation theory problems go, will be enough to guarantee the condition of surjectivity. So why is this a good lemma? So let me write the upshot is that summing up, given E dot in L3 dot F a morphism in p minus 1, 0, or x. The condition that locally it is of the form let me call this f to I pull back omega my with f to I mod I squared surjective is equivalent to if I replace by requiring that this co-kernel, which again doesn't depend, that for any x in x, the co-kernel of x pullback of Hom C, x pullback of E0 C, 2 Hom C, x pullback of E minus 1 C is an obstruction space for x over y at x, because this gives me an injectivity on the dual, which is an injectivity on the co-kernel, which corresponds to a surjectivity on the kernels, because we are just working on vector spaces, finite dimensional vector spaces. So we are not really losing any information. And so here, this condition is so the point is this condition, which looks extremely abstract, is in fact a condition which is very easy to verify once you know the formation theory. In particular, you don't have to invent a complex yourself. And by now there is, like the way Harjon writes, there is even a book by Harjon not so many years ago about the formation theory, because reading the original reference by Lucy can be a bit unpleasant. But in fact, I think the best place, if you are interested into learning the formation theory, the place where I really understood the basics was a volume of Tata lecture series from Michael Artin, and he has extremely beautiful notes. So you can read it wherever you want, but that's really where I learned, because it's an you would think, I mean, Michael Artin is the person who invented Artin stacks. You would think he's somebody who cannot be concrete, but in fact these notes are incredibly concrete and very, very readable. After you, even if you just read the beginning, afterwards you will feel extremely confident, and the beginning is totally elementary. I mean, I promise that you can give it to beginning graduate student and they will find their way through. And it will lead them to, it's a good, because it kind of writes out for you what flatness means, for instance, which I found helped me a lot. So understanding the relationship between flatness and this infinitesimal extension I found very, very useful. Anyway, so the point is that altogether, if we believe that all we need to do is check something locally and trust the Ling to do the gluing for us, then we have an understanding of what we are looking for. We are looking for a complex which maps to this L-twiddle, which is perfect in -1, 0, which means whenever I have an incarnation in which the right hand, the degree 0 part is locally free, the other one is also locally free, and that it gives me an obstruction space. Okay, and that's it for today. Tomorrow there's the colloquium, and on Thursday we will say, so just for preview, on Thursday what we will do is I will tell you that you don't need to read what Deligne writes. I mentioned it a bit to tell you where the idea comes from, but we will do directly the construction in the case we are interested in, and the only case of quotient stacks we will need is the quotient by a group action, and all I will assume you know is if you have, I want you to know, given a scheme, what it means to have a group scheme over that, and given a group scheme over something, what it means to have a principal homogeneous space. So if you know, and what is an action of a group scheme over a scheme, I mean that, so the group scheme theoretic version of what is a group and what is a principal homogeneous space and what is an action of a group on a set. If you understand this, you will understand enough stacks for all the purposes we have. So it is really the most elementary case of stack. And we will see that it does what we want it to do. Okay, so thank you very much.